Infinity. For over 2,000 years, infinity has baffled the minds of many mathematicians, scientists, and philosophers across the globe. But what is it? How do we use it? And how do we get from thinking about the infinitely big to the infinitely small? These are questions which have puzzled the greatest minds for thousands of years. This is From Infinity to Infinitesimal. If you look up the definition of infinity on Google and look under mathematics, you will find it says a number greater than any assignable quantity or countable number. But is this true? There is a great debate on whether infinity is a number or not, and really it comes down to the definition of infinity and the definition of a number. However, most mathematicians would argue that infinity is not a number because of how it behaves. One way mathematicians think about infinity is using the idea of a hotel with an infinite number of rooms, with each room numbered with a natural number. A natural number is a number used for counting, so it must be positive and whole, for example 1, 2, 3, etc. There are an infinite number of natural numbers. We call this hotel Hilbert's Hotel because David Hilbert is the person who came up with the idea. We can imagine that one night the hotel is completely full with an infinite number of guests. For any hotel to be full, each room needs to have a guest in it. Let's assume that each room is a single room. And this is still true for Hilbert's Hotel. Basically, we are pairing each guest with a room. This is the principle of counting. If we have a theatre with 20 seats and we want to know if there are 20 people in the room, we can either count each person or we can get each person to sit down on a seat, pairing each person with a seat. This pairing is called a function in maths. If, when they are all sat down, we don't have two people at one seat, we would say the function is injective. And if we use every seat, we say the function is surjective. So, if every person has a seat and we have a surjective and injective pairing, which means that each seat only has one person and every seat is used, we have a perfect pairing because each person will have a seat and no seat will be used more than once. Therefore, we have exactly 20 people. This is called a bijective function. Every time we count, instead of matching the items which we want to count with seats, we are matching them with the natural numbers. When we pair a set of objects and have a perfect pair, we say the two sets have the same cardinality. So basically, they contain the same number of objects. So, back to our hotel. When we say the hotel is full, we are saying that every room has a guest. So as long as no guests are left over, every guest has a room and the hotel is full, we can say that there are the same number of guests as rooms. So the set, which is a group of guests, and the set of rooms will have the same cardinality. But what happens if Hilbert's Hotel is full and another guest comes along? You might say that we could put the guest in the last room, but what number is the last hotel room? For every person to have a room, they need to have a room number, because we need to be able to match them up with a room. So, instead, what we can do is move everyone up one room. So the person in room 1 moves to room 2. The person in room 2 moves to room 3. If we call someone's room number M, they will go to room number M plus 1. Then, the first room is free, so the extra guests can fit into room 1. So what we were saying is that the set of natural numbers has the same cardinality, which is the number of objects in the set, as a set of natural numbers plus 1. So a set with an infinite number of objects has the same number of objects in it as a set with an infinite number of objects plus one object. If we put this into an equation, we get infinity plus 1 equals infinity. However, if we take infinity from both sides of the equation, we end up with 1 equals 0, which isn't true. This evidence suggests that infinity doesn't act like a number. So, back to our hotel. We can use this method for any finite number of guests. We just move the hotel guests up that number of rooms. If 3 guests come along, we just move the hotel guests up 3 rooms and fit the extra guests into the first 3 free rooms. So, any finite number plus infinity has the same cardinality as the original infinity. But what happens if a busload of an infinite number of people come along? Can we fit them into the hotel? Well, what we need is 2 types of natural numbers, one which the people in the hotel can go to, and one which the people in the bus can go to. So, our 2 types of numbers could be odd and even numbers. An even number is a multiple of 2, and an odd number is a multiple of 2 minus 1. So everyone in the hotel could go to the even numbers. We could do this by making them double their room numbers. So the person in room 1 goes to room 2, the person in room 2 goes to room 4, and so on. The person in room N would go to room 2M. So, each hotel guest still has a room number, but the odd numbers are free. Now, we could ask everyone on the bus to take their seat number, double it, and minus 1. So each person on the bus will go to an odd room number. So the person on seat 1 will go to room 1, because 1 times 2 is 2, and 2 minus 1 is 1. The person in seat 5 will go to room 9, because 5 times 2 is 10, and 10 minus 1 is 9. The person in seat N will go to room 2N minus 1. Therefore, we have matched every person with a room number, with no room being used twice, which means it's an injective function, and we have used every room. So it is a surjective function. So infinity plus infinity has the same cardinality as infinity. If we put this into an equation, we would get infinity plus infinity equals infinity, which is the same as 2 times infinity equals infinity. However, if we minus infinity from both sides of the equation, we get infinity equals 0, which is definitely not right. This is further evidence that infinity is not a number. You may have heard of the book or film The Fault in Our Stars, in which Hazel says,
I'm going to talk about math. I am not a mathematician, but I do know this. There are infinite numbers between 0 and 1. There's 0.1, 0.12, and 0.112, and an infinite collection of others. Of course, there is a bigger infinite set of numbers between 0 and 2, or between 0 and a million. Some infinities are simply bigger than other infinities.
However, there are 2 times as many numbers between 0 and 2 as there are between 0 and 1, because there are the same number of numbers between 0 and 1 as there are between 1 and 2. However, if we go back to our equation 2 times infinity equals infinity, we can work out that there are the same number of numbers between 0 and 1 as between 0 and 2. There are also the same number of numbers between 0 and 1 million. If 1 million buses with an infinite number of people on them came to the hotel, assuming it was empty, the people in the first bus could go to all the rooms divisible by 1 million, by multiplying their seat number by 1 million. The people in the second bus could go to the numbers which are a multiple of 1 million, but plus 1, and the people in the third bus could go to the rooms which are a multiple of 1 million plus 2, etc. This would work for any finite number. So, sorry Hazel, but there are the same number of numbers between 0 and 1 as there are between 1 and a million. So, what happens if an infinite number of buses, each with an infinite number of people in them, come along, apart from worse traffic than London at peak times? Well, another way to match the room numbers to the guests is to make a list with each guest on it. If we had all the time in the world and we could make a list of each guest, we could just put the first person on the list in room 1, the second person in room 2, and the nth in room M. That way, everyone would have a room number, and if the list was infinitely long, each room would be taken up. So how do we list the people in the buses? Well, we can do it like this. If we have a table of bus number and seat number, where bus 0 is the guests already in the hotel, and the seat number will be their room number, we can make a pattern through all the people, like this. So, the first person my pen goes through will be in room 1, the second in room 2, and the third in room 3, etc. As long as we can extend this pattern for any bus number and seat number, which we can, we will just need an infinitely huge piece of paper. We can say that the cardinality of the people pairs with the cardinality of the rooms. So, there are the same number of people as there are rooms. You might ask what this means. Well, we could say that the bus number is the numerator of a fraction, and the seat number is the denominator of a fraction. We have then matched each fraction up to a room number, and this means that the set of natural numbers has the same cardinality as the set of positive fractions. So, there are the same number of fractions as natural numbers. But what happens if some guests come along, each wearing a t-shirt with an irrational number on? Are there the same number of irrational numbers as natural numbers? An irrational number is a number which cannot be written as a fraction, so the digits after its decimal place continue forever without repeating. Well, a famous mathematician called George Cantor proved that the irrational numbers couldn't be listed, and so couldn't be matched up with the natural numbers. He did this by assuming that we already had a list of all the irrational numbers. Let's say we had the list of all the irrational numbers between 0 and 1, so my list could start something like this. Cantor's argument is called the diagonal argument because what we do is we take the first digit after the decimal place of the first number, then the second of the second number, the third of the third, which forms a diagonal line. But we add 1 to each digit, so 1 goes to 2, 2 goes to 3, 9 will go to 0, etc. Now we have another irrational number. However, this number varies from all the other numbers because it has at least one digit different. So we have made a completely new number which isn't on the list. So this means that we can't make a list of all the irrational numbers, and so we can't fit them into the hotel. This means that there are more irrational numbers between 0 and 1 than whole numbers between 0 and infinity. The reason that we can't fit the irrational numbers into the hotel is because Hilbert's hotel deals with an infinity called Countable Infinity, which is the cardinality of the set of natural numbers. However, the set of irrational numbers has a cardinality of a bigger infinity. We call an infinity bigger than countable infinity uncountable infinity, so at least Hazel was right when she said that some infinities are bigger than others. So far, we have been thinking about infinity cardinally, which takes into account the size of sets. However, we can also think about infinity ordinally. This takes into account the order in which we do things. For example, we all know that 1 add 2 is 3, and 2 add 1 is 3. The order in which we add the two numbers doesn't matter. However, with infinity, it does. We can imagine that we are having a party with an infinite number of guests. When each guest arrives, we give them a raffle ticket from a raffle ticket book with every natural number in it. So, the first person will have the raffle ticket with 1 in it, the second with 2, the third with 3, and so on. Their raffle ticket number will determine their place in the queue to the bar. So, if each guest comes along with a natural number on their t-shirt, we can give them all a ticket. Once all the natural numbers have come along, all the tickets in the raffle booklet will have been used up. If one guest comes along before all the natural numbers, they will have the first ticket, and the natural numbers would have the ticket after their number. However, what happens if another person comes along after all the tickets have been handed out? We can't ask everyone to move up one ticket and let the person who came last go in front of the queue, because that wouldn't be fair. And we can't put them with the last ticket because the booklet has already been used up. So what we need to do is get a new booklet of raffle tickets, for example in a different colour, e.g. blue. And remember that all the blue tickets come after the original booklet of raffle tickets. So this means that ordinarily, infinity plus 1 doesn't equal 1 plus infinity. This is even more evidence that infinity is not a number. So what is it, you might ask? Well, many mathematicians would argue that infinity is a concept as opposed to a number.